In the previous section, we showed that a swimmer submerged in a pool feels a force perpendicular to the surface of her body due to the pressure from the water. We will now use Newton's second law to show that the pressure in the water, or any fluid for that matter, is a function of depth. More specifically, the pressure in a fluid increases as we go deeper in the fluid. The figure shows a container of fluid where we have focused on an arbitrary rectangular column of fluid within the container. The column has a cross-sectional area A and a height h. Let's draw the free body diagram for the vertical forces that act on the column. There are three forces. One of the forces is the weight of the column, which acts at its center of mass, and the other two forces are due to the pressure in the fluid. Pushing down on the top of the column is a force equal to P1 times A, where P1 is equal to the pressure in the fluid at the top of the column. And pushing up on the column is the force P2 times A, where P2 is the pressure in the fluid at the bottom of the column. Since we are assuming the fluid is static, the column must be in equilibrium. Therefore, the sum of the forces in the y direction must be equal to 0. If we divide this equation by the area A, we get the following. This shows that P2 is greater than P1 by an amount equal to mg over A. Qualitatively, we understand that P2 is greater than P1 because the force acting on the bottom of the column must support the weight of the fluid above it. We can write the mass of the column of fluid in terms of its density and volume, and since the cross-sectional area is constant, the volume of the column will just be equal to this area times its height. We can make this substitution into our equilibrium equation, and we find that P2 is equal to P1 plus rho gh. This relationship indicates that if the pressure P1 is known at a higher level, the larger pressure P2 at a deeper level in the fluid can be found by adding the amount rho gh. In determining the change in pressure, we have assumed that the density rho is the same at any vertical depth h, or in other words, the fluid is incompressible. This is a reasonable assumption for liquids, since the bottom layers can support the upper layers with little compression. However, in gases, the lower layers are compressed substantially by the weight of the layers above. This is why, for example, that the Earth's atmosphere is more dense near the surface of the Earth than at higher altitudes. It is important to stress that the change in pressure in a fluid at different depths depends on the vertical distance h in the fluid and not the horizontal distance. Therefore, the pressure at the same depth in different containers will be equal, independent of the cross-sectional area of the containers. This figure demonstrates that the pressures at points A, B, C, and D, which are all at the same depth, will be equal, even though their containers all have different cross-sectional areas. In the next section, we will investigate common devices that are used to measure pressure.